Hi everyone. I'd like to spend a few minutes talking through each question on this practice quiz to help answer any questions that you had to make sure that you're feeling good and prepared over all of our quiz topics. So feel free to pause the video if needed, rewind to rewatch sections, or fast forward to jump to certain problems that you need. So starting with number one, so this is what we started with on our first day of Chapter 3, 3.1. We're solving the system of equations by graphing, which means we are looking for the point of intersection between these two lines. So I'm going to talk about a couple of graphing techniques that we can use based on the original form of the equation. So our first equation is in the form of y equals mx plus b. So we can see here that our y-intercept is 3, and our slope is negative a fourth. So negative slope goes down like this. Rise over run is up 1 over 4. So you can follow the pattern to make another point in the other direction. However, we really just need 2 points. Whoa, sorry. See if I can make that line a little better. It's really helpful if you have a ruler to go through these. All right, for our second equation, it's not in slope-intercept form. The x and y are together on the same side. We actually call that standard form. So instead, I'm going to use the other method that we have talked about this chapter is finding the x-intercept and the y-intercept. So first, I'm going to find the x-intercept by covering up y, meaning if y is equal to 0. So we have the equation 4x equals 8. If we divide both sides by 4, we get x-intercept is 2. Okay, I'm going to do a similar thing to get the y-intercept. That's when x is equal to 0. Don't forget about that negative sign. So we have negative 4y equals 8. Divide both sides by negative 4, and we get the y-intercept to be negative 2. All right, so we are going to connect x-intercept of 2 and y-intercept of negative 2. And we can fill in some other points. If you look at the slope between them, up 2 over 2. So that simplifies down to up 1 over 1. And it's going upward, so it looks like we have a slope of positive 1. Let's continue that pattern, up 1 over 1, up 1 over 1, and look, right here is the point that they share. We don't even really have to connect these. I'm still going to, but we can see already that that's going to be our solution because it's the point of intersection. So we're going to want to look for the x-coordinate of that point, which is 4, and then the y-coordinate of that point, which is 2. Remember, you can always check to see if something is a solution by plugging in the x value and the y value into both equations and making sure that it makes both equations true. All right, the next two problems we also talked about in 3.1. So we want to determine if they are independent, dependent, or inconsistent. So we can always do a little bit of work with our equations. We could turn them into slope-intercept form to compare the slopes to see if they're parallel, to just compare them in general to see if they're the same line, or we could be able to tell if they are different lines. So let's look at the first equation here. I'm going to start by adding 2x to both sides, and then I'm going to divide everything on both sides by 2. So 2y divided by 2 is y. 2x divided by 2 is 1x minus 9 divided by 2, you can write that as 9/2. You can even write it as a decimal, 4.5. All right, let's look at the second equation. I am going to start by subtracting 2x from both sides and then dividing everything on both sides by negative 2. So negative 2y divided by negative 2 is y. Negative 2x divided by negative 2 is 1x. Negative 11 divided by negative 2, so negative divided by a negative is a positive. 11 divided by 2 is 5.5. All right, so what I notice here is that this line has a slope of positive 1, this line has a slope of positive 1, but see they have different y-intercepts. And what do we know about lines that have the same slope? they are parallel. And if they're parallel, they're never going to cross, they're never going to intersect, and so this one is no solution. And the name for that is inconsistent. So it's important that you know inconsistent as well as that it's no solution. So that's one way we could have approached it. Another thing that you could have done, based on the way this is nicely set up, you could just put them together thinking about that elimination method, because look, everything eliminates. These are going to cancel, those cancel, you're left with 0 on one side. When you add the numbers together on the other side, you don't get 0, we get negative 20. The variables cancel out. It's a false statement, which is another clue that it's no solution and that it's inconsistent. So that second method, I think that would be a little easier. It's less work than doing all the algebra to turn it into slope-intercept form. But I just want you to be aware of different methods that you can use. Okay, for the next one, number 3, so I would probably still think about putting the second equation in slope-intercept form. The first equation is all ready to go. So let's start by subtracting 3x from both sides, and then divide everything by negative 3. Look, it's the same equation, x plus 5, x plus 5. So because it is the same line, it's an infinite number of solutions, and we call that situation dependent. Now, if we ended up with two different lines, different slopes, different y-intercept, it would be independent, and that would just be one solution. So that's like the first problem that we did. That one was independent. Okay, number 4, solve the system by substitution. So this one, in the second equation, it gives us an equation in the form x equals. So x equals 3y minus 13. So we're going to plug that in for x into the first equation, making sure that you're using parentheses when you plug it in. And then we're going to continue solving this equation for y. So we'll go ahead and distribute the 2. Combine like terms, so 6y minus 3y is 3y. Don't forget about negative 26. And we'll keep solving, add 26 to both sides. And divide both sides by 3. We get y is 5. So that has just told us the y value of the point of intersection. Now we can plug that y value into the second equation to easily solve for x. And we get that our x value is 2. It wants us to write our solution as an ordered pair. It's 2, 5. If we were to graph this, those would be the coordinates, or that, yeah, those would be the xy coordinates of the point of intersection. All right, number 5, we're going to solve this system using elimination. So what would probably be easiest on this one is to eliminate x, because we only have to change the top equation. So if we multiply everything in the top by negative 6, we get negative 6x minus 30y equals 126. Keep everything in the bottom equation the same. And when we add them together, minus 6x plus 6x is going to cancel. Minus 30y plus 4y is minus 26y. 126 plus 30 is 156. All right, and then let's divide both sides by negative 26, and that works out nicely to equal negative 6. So again, that's the y value of the point of intersection. You can plug it back into either one of your equations. I'm just going to plug it back into the first one. Let's add 30 to both sides. Negative 21 plus 30 gives us the x-coordinate of 9. Okay, next we have a word problem. We want to write and solve a system of equations. Now we don't want to confuse this with the linear programming process that we've just learned about recently. So this is just a regular word problem. It's just two equations that we're solving. There's not as much information given to us as we have in linear programming. So we are just trying to figure out just how many boxes of oranges did he sell. But there's also boxes of grapefruit. So I'm going to use O to represent the number of boxes of oranges. I'm going to use the variable G to represent the number of boxes of grapefruit. And you can use X and Y. That's fine. Just define your variables in your first step, so tell me which one each represents. Okay, so he sold a total of 562 boxes. So let's write out O plus G equals 562. Okay, then our next equation will have to do with the amount of money. So it's $11 for a box of oranges, $10 for a box of grapefruit. Altogether, that's going to cost $5,977. All right, that's it. So those are the two equations. You can solve using substitution or elimination. I'm going to do elimination, multiplying everything in the top equation by negative 10. So that's going to give me negative 10O. Maybe I shouldn't have used O because it kind of looks like a 0. I'm going to put a little line through the 0 in 10. Sometimes you'll see zeros written that way. All right, so negative 10O minus 10G equals 5,620. So don't forget to add a 0 on the end of that. All right, second equation is going to stay the same. Okay, so adding these together, we're going to get 1 times O. Boxes of grapefruit, those are all going to cancel. And, oh, I just realized that this was supposed to be negative, so don't forget about that negative sign there. So really I'm going to think about doing 5977 minus 5620. All right, and that gives me 357. Oh, this looks very confusing. I wish that I didn't use O. Maybe we should have used X and Y. But the number of boxes of oranges is equal to 357. Now, if we know that the total has to be 562, I would just subtract 357 plus 562, and we see the number of boxes of grapefruit would have to be 205. Now here's the thing, it's just asking us how many boxes of oranges did we sell, so we can just write this for our answer, 357 boxes. Okay, next we're going to graph the solution to the system of inequalities. So we're going to graph each inequality separately. We're going to use those teeny tiny shading arrows to tell us the direction the shading will be, but ultimately we're just concerned about where the shading overlaps. All right, so for our first inequality, that's going to be based on the boundary line y equals negative 1x minus 2. It's got a slope of negative 1 and a y-intercept of negative 2. Now, because it's just a less than symbol, we're just going to connect those with a dotted line. So make sure you're always thinking about, is it dotted line or is it a solid line? Now, if we do the test point of 0, 0, you're going to think about plugging in 0 for x and y into the original inequality, and we get 0 less than negative 2, which is false. So that means that we're going to shade away from 0, 0. that means that 0, 0 is not a solution, and all the other points on the same side are also not solutions. So that means that the solutions have to be on the other side. Okay, for our next inequality, we can use the boundary line y equals 1/4 x plus 1. So it's got a y-intercept of 1 and a slope of 1/4. And because it's greater than or equal to, that means that we can connect it with a solid line. Oh, my line's not very straight, but hopefully yours is better than mine if you used a ruler. Let's plug in that test point of 0, 0. So we've got 0 greater than or equal to 1/4 times 0 is 0. So we're left with 1. This is also false. 0 is not greater than 1. So we also have to shade away from 0, 0, which in this case means that we're shading above the line. And now we just have this teeny tiny section where the shading overlaps. It's just going to be right here. That's the only part that we actually want to shade in that represents the solution to our system. All the points in that region make the first inequality true. They also make the second inequality true. All right, area of a parking lot, 600 square meters. A car requires 6 square meters while a bus requires 30 square meters. The attendant can only handle 60 vehicles. If a car is charged $2.50 and a bus is charged $7.50, how many of each vehicle should be accepted in order to maximize profits? So this is going to be a linear programming problem. If you ever see the word maximize or minimize, it's linear programming. If you don't see that word, like the orange and the grapefruit problem, then it's not. So let's assign our variables. What are we dealing with this time? We're dealing with cars and buses. Let's let C represent the number of cars. Let's let B represent the number of buses. P can represent profit. All right, so let's think about some of our constraints. It says the attendant can only handle 60 vehicles. So the number of cars plus the number of buses must be less than or equal to 60. Another constraint is the area of the parking lot. It's 600 square meters. A car requires 6 square meters, while a bus requires 30 square meters. So all of that must be less than or equal to 600. The other constraints that are implied is that it has to be a positive number of cars and buses. All right, objective function has to do with profit. So the profit for a car is $2.50 per car. For a bus is $7.50 per bus. All right, let's think about our graphs. So if you go to our first inequality, let's find the intercepts. The C-intercept is 60. The B-intercept is also 60. If we think about shading, plug in the test point of 0, 0. Is 0 less than or equal to 60? That's true, so we're going to shade towards 0, 0. All right, for our next line, let's find the B-intercept. Divide both sides by 30. And so 600 divided by 30, that's going to be 20. So the B-intercept is 20. And then if if B is 0, so cover this up and divide both sides by 6, and we get the C-intercept is 100. Plug in the test point at 0, 0. We get 0 less than or equal to 600. That is true. So we're going to shade toward the test point of 0, 0. If C is greater than 0 and B is greater than 0, it's going to look like this, keeping everything in the first quadrant. And we'll go ahead and shade where they overlap. So we've got 4 vertex points. And we can start to list those. out in our table. So we're going to put cars, the C value first, buses second, so keep it uh, with like where the X and Y would be. So X comma Y, but this time it's C comma B. So our first vertex point we have 0, 0. The next one we have 0, 20. The next one down here is 60, 0. And the last one is the one that we have to solve for. So we have to solve the system of equations that created that intersection point, and that system is based on the constraint inequalities over here. But we're going to turn these into equations because it's really the system of equations of the boundary lines before we did the shading. You can solve that system using substitution or elimination. I'm going to do elimination. I'm going to multiply everything in the top equation by -6. All right, adding these together, I wrote a B where a C is supposed to be. Sorry, I'm getting very tired. Okay, this is a C. All right, so we can see that our C's are going to cancel. So 6C minus 6C, those cancel. 30B minus 6B is 24B. 600 minus 360 is 240. Let's divide both sides by 24. We get B is 10. All right, so 10 buses. And if the total has to be 60, or if the total can be 60 at the most, we'll do 50 cars. Okay, finally to figure out the profit, so let's rewrite the objective function. So $2.50 per car plus $7.50 per bus. So make sure that the first letter that's listed is the first letter that shows up in your equation. So you're putting the right numbers in the right spot. So of course the first combination of 0 cars and 0 buses is probably not very helpful. That's going to be a profit of $0. The next combination is 0 cars and 20 buses. So 2 times 7.5 is 15. Let's add a 0 on the end, so that should be a profit of 150. Okay, the third combination is 60 cars and no buses. Okay, so that's also a profit of 150. All right, our last combination is 50 cars and 7 buses. All right, so it looks like that's going to be our best combination, $200. Yes, and we're wanting to maximize our profit, so we're looking for the highest amount. So that's going to be 50 cars and 10 buses for a maximum profit of $200.